my channel, children. Today I am going to introduce to you some terms used in coordination compounds. Coordination entity. Now, coordination entity constitute central metal atom or ion and the ions or molecules surrounding it. Here you can see whenever you see a complex, whatever enclosed in the square bracket is coordination entity. Now here, I can give you one more example. K2NiCl4. If you have a complex like this, only NiCl4 is the coordination entity. This is coordination entity. Now what is central metal atom or ion? In this complex, central metal atom is Ni. In this, it is Ni. If you look at the other example, NiCl2 H2O 4 times. Central metal atom is Ni. Or if I say in the form of ion, it is Ni plus 2. Here in this complex, CO is the central metal atom or ion CO3 plus. In FeCN6 3 minus, Fe is the central metal atom or Fe3 plus is the ion. How did I get this charge on the central metal atom? I am discussing in my next video. You can see that. Ligands. Whatever surrounding the central metal atom, Ni is surrounded by Cl2 and H2O, right? Both these are ligands. Cl, NH3 are the ligands. Here, Cl is the ligand. If I take this complex, two types of ligands, Cl and NH3. So, what is surrounding the central metal ion? That is the ligand. Here, there can be simple molecules like Cl minus, or it can be even larger molecule like CH2, NH2, CH2. This is ethylene diamine or ethane 1,2-diamine. This is in short, that is a big name, right? So we in short write it as EN, ethylene diamine. Here, this is also a larger molecule. So any larger molecule which can donate a pair of electron, or any small molecule which can donate a pair of electron is a ligand. So the main criteria of ligand is donating a pair of electron. A ligand should be able to donate a pair of electron to the central metal ion. So when a ligand donates a pair of electron to the central metal ion, what will happen? Bond is formed. What type of bond? It is coordinate covalent bond. So the bond formed in coordination complex is coordinate covalent bond. Now, classification of ligand. Which are the types of ligands? Ligands can be classified based on the charge, either based on charge or based on the donor site. If it is based on charge, you can classify into negative ligand, positive ligand, neutral ligand. You can see the example. Cl minus, F minus, NO2 minus, Cn minus are all negative ligands which can donate a pair of electron. Here, NO2 plus, NO plus, N2H5 5 plus are all positive ligands which are also having a pair of electrons to donate. Neutral ligands, H2O, NH3, CO, NH2OH are all neutral ligands, ligands that don't carry either positive or negative charge, which can donate a pair of electrons. Now, another classification is based on donor site. If a ligand can donate only one pair of electron, then it is monodentate. If you look at H2O, there is only a pair of electron it can donate. NH3, only one pair of electron it can donate. If you look at the second example, ethane 1,2-diamine or ethylene diamine, it can donate two pair of electrons. Ethane 1,2-diamine can donate. There are two nitrogen atoms. So each nitrogen atom can donate a pair of electron. So it is called a bidentate ligand. If there are three sites to donate a pair of electron, then it is called tridentate ligand. So more than two sites are there in one molecule to donate electron, then it is called a polydentate ligand. A ligand which has 6 sites to donate pair of electron is hexadentate ligand, and the example given here is EDTA. EDTA, ethylene diamine tetraacetate. EDTA is an example of the ligand that can donate 6 pairs of electron. It is an hexadentate ligand. Now, what are chelating complexes? Now you can see here, some ligands can donate more than 2 pair of electron, isn't it, children? So you can see here ethylene diamine, it can donate 2 pair of electron. If a complex is having only a bidentate or tridentate ligand, then it forms a chelate complex. Such ligands are called chelate ligands because it forms a cage-like shape. Ambidentate ligand. Ambidentate ligand, single ligand can donate through two different sites. This I am again telling in my next video. A single ligand can donate to through sites. Here NO2. Here NO2 is an ambidentate ligand. It can ligate either through N or through O. Here it can ligate to N or through O. But it can ligate, it can donate only a pair of electron. Now SCN, thiocyanate or sulfocynato, you can see S, it can donate electron, or N, it can donate electron. Another example is CN and NC. C can donate electron or N can donate, or not both. Okay, any one can donate electron. So in the molecule there are two sites which can donate electron. Such a ligand is called ambidentate ligand. Now I will just tell you what is this chelate complex. Okay, here let us see this. Monodentate ligand, I gave you the example, CH3NH2. Only one pair of electron. Cl, only one pair of electron, right? H2O, only one pair of electron. Monodentate. Bidentate means it can give two pairs of electron. CH2NH2, ethylene diamide, CH2NH2, two pairs of electron. This is a bidentate. Now, when a bidentate ligate with a central metal ion, ligate, we use the word ligate, N is giving electrons to the central metal ion, it's forming a complex, it's forming a coordinate covalent bond. One more molecule I am going to write here, CH2, NH2, N is ligating, N is only having a pair of electrons, so N only will ligate, okay. NH2, N is ligating. Such complexes in which the bidentate or tridentate ligand is ligating with the central metal ion is called a chelate complex. You call it chelate. Or the ligand is also called a chelate ligand. Okay. Chelate complexes are very, very stable. Now, if I write a complex with monodentate ligand, you can see cobalt. Here. Cl, arrow will come to cobalt only. Cl is giving a pair of electron. Okay, 2Cl giving a pair of electron, forming a coordinate covalent bond. Then H2O giving a pair of electron. 2H2O, 2NH3 giving a pair of electrons. 2NH3 giving a pair of electron. Okay. Now here, when I write the formula of the complex, how will I write? Here I can write as Ni. Instead of CH2, CH2, NH2, NH2 is such a big formula. In short, we can write it as En. It is agreed by IUPAC. En. 2 ethylene diamine is there. So I write it like this. 2 ethylene diamine. Here I will write the complex as CO. 2NH3 is there. 2H2O is there. And 2Cl is there. Okay. Here I am writing plus. I am giving the charge for this 3 plus. Charge of central metal ion I am discussing in the next video. Now, the next term is coordination number. What is coordination number? Here in book they have given the definition as number of ligand donor atom to the central metal ion that is directly bonded. Number of ligands surrounding the central metal ion is coordination number. But here when you have to count the number of bonds surrounding the central metal ion, that is coordination number. Now if you look at this complex NiCN2, when you look at it you think it is only 2 ligand, but actually there are 4 bonds. So in this case the coordination number is 4. In this case, if you take this case, how many ligands are there? How many bonds are there? 1, 2, 3, 4, 5, 6. 6 bonds. So in this case, coordination number is 6. Monodentate ligand means you can directly count the number of ligands. Bidentate means number of ligands into 2. Tridentate means number of ligands into 3. Okay. So coordination number will be the number of coordinate covalent bond that a ligand forms with the central metal ion. So count all the coordinate bonds, you will get the coordination number. Now look at this example. In PTCl6, Cl is a monodentate ligand, so coordination number is 6. In NiNH3 4 times, NH3 is a monodentate ligand, so coordination number is 4. Now we will go to the next term, coordination sphere. What is a coordination sphere? So here coordination sphere is When you write the coordination entity, if there is a charge over the coordination entity, you call it coordination sphere. For example, look at this complex K for FeCN6. If you write FeCN6 4 minus with the charge, then it is coordination sphere. Okay. Now, coordination polyhedra, the spatial arrangement of ligands which is directly bonded to the central metal ion is called coordination polyhedra. You are mainly studying three coordination polyhedra: octahedral, tetrahedral, and square planar. If the coordination number is 6, then you get octahedral. If the coordination number is 4, you get tetrahedral or square planar. Okay. Now, so you know what is coordination polyhedra. Now, oxidation number of central metal ion. Oxidation number is the charge carried by the central metal ion. You can see here CuCN4 3 minus. What is the charge carried by the Cu? The charge carried by the Cu is +1. That +1 is the oxidation number of oxidation number of central metal ion. Now, how to calculate the charge carried by the central metal ion? That I am discussing in the next video. You can see that before nomenclature I am explaining that. So whatever charge carried by the central metal ion is the oxidation number of the central metal ion. In this case, how it is calculated, just a hint I will give. Cn is -1, -1 into 4 is -4. Outside it is -3. So we don't know what charge. So put x plus 4 into -1 is equal to -3. So x will be equal to -3 plus 4, that is +1. So charge carried by Cu will be +1. Now look at this complex. What will be the charge? FeCN6 4 minus, we don't know. So put x plus 6 into -1 is equal to -4. What is x equal to? -4 plus 6. So x is equal to +2. So charge carried by Fe is +2. That is the oxidation number of the central metal ion, and it is always written in bracket. Now let us go to the next term. Homolyptic and heterolyptic complexes. Complexes which have only one type of ligand is called homolyptic, and complexes which have two type of ligand is called heterolyptic. Okay, so CONH3 6 times is homolyptic, CONH3 4 times Cl2, two types of ligand, that is heterolyptic. Now let us just recall what we have studied. So I'm just writing a complex in K4FeCN6. If I remove 4K plus 1, 4K, I can write, if I write this alone, this is coordination entity. Now if I put the charge -4, this is coordination sphere. Coordination sphere. Fe is the central metal ion. This is the central metal ion. Cn is the ligand. It is a monodentate ligand. Coordination number of this complex, it is a monodentate ligand. It has 6 monodentate ligands. So coordination number is 6. Right? Now, coordination polyhedra. What is coordination polyhedra? The shape, the three-dimensional arrangement of the ligands around the central metal ion. It is octahedral. Coordination number 6 means you have only octahedral. So you have, this is the coordination polyhedra, octahedral shape. Now this ligand, as this complex has only one type of ligand. So what type of complex it is? Homolyptic. Homolyptic complex. Right? Now I'll give you another one. COEN 3 times 3 plus. Okay. Now here, if I write the square bracket alone, that is, what is that called? Coordination entity. If I put charge along with it, it is called coordination sphere. Now CO is central metal ion, En is the ligand. En is ethylene diamine. In short, we write En. It is agreed by IUPAC. What is coordination polyhedra? CO. It is a bidentate, right? Coordination polyhedra is octahedral. So I am not going to write CH2 NH2. It is very hard for me. It will take too much of time. I will simply write En. You can also write like this. This is the easy way of representing. How many bonds are surrounding the central metal ion? 1, 1, 2, 3, 4, 5 and 6. Coordination number is 6. This is also a homoleptic complex. Now heteroleptic complex example, I will write CO, NH3, thrice, Cl3. This is a heteroleptic complex. And this is only square bracket and central metal ion. This is also called coordination entity. These are the terms we have done in today's class. Thank you, children. I will be posting a link. You can download the notes from the link. Okay.